Okay, so let's say that we have this parabolic function that looks like this, but we're not going to look at the whole parabola. We're only going to look at the parabola from this interval here, from -1 to 2. Right away, I want to show you or point out that this is an x-coordinate, and so is this. You see, this is not x and y, this is x, and this is also x. So the viewing window would be from this x-coordinate to this one. So for the sake of eliminating distractions, I'm going to get rid of the portion of the parabola, the portions of the parabola that are completely irrelevant. I'm only going to look at the parabola from this snippet, from this x-coordinate to this x-coordinate. How could I have gotten the y-coordinate of 4? You take -1 and you plug it in there. You take 2 and you plug it in there to get back their respective y-coordinates. So this is an endpoint and this is an endpoint. What I want you to see is that if I connect the endpoints together with a line, let me see how I can draw this. This guy here, that's called your secant line. And if you're interested in writing the equation of the secant line, let's do it. So this is my secant line, and it has these 2 points here. So I have this point and I have this point. Let's find the slope m between 2 given points. So we can go y2 minus y1, right? So I want y2 minus y1 over x2 minus x1. So carefully do that, and you get -3 over 3, which is -1. So my slope of this secant is -1. Now I need a point. If I want to write the equation of a line, I need a point and I need a slope. This is my slope. Now I need a point. Well, I have 2 points to choose from. Pick either point, it doesn't matter. Suppose you select this one. Let's go point slope. So we'd go y minus y1 equals m times x minus x1. And if you want to distribute and simplify, you would get -x, that's +2 plus 1. So this here, this is your secant. That's your secant line. That takes care of that. Now, what exactly does MVT, the mean value theorem, what does it tell you? It says that if you're dealing with a shape or a function that is continuous and differentiable within a certain interval, and if A and B, if the points are not on the same level, right, like one is above and one is below, whatever, then you're guaranteed this. You are guaranteed that there is going to be a point that is red. And this point that is red is going to be somewhere between here. It's going to be somewhere between -1 and 2. It's going to be some number in here. I think usually the textbooks call it the number C. There is going to be some number C that is between here and here, such that the point at C, let's just pretend that it's like right here. What would happen is you go to the specific location where at that point there, your tangent line is going to be parallel to your secant line. That's the whole point of MVT. It means you're guaranteed a point somewhere in the middle that if you go and stop, that if that's your point of tangency, then your tangent line is going to be parallel to the secant line. And the secant line is the line that connects the beginning with the end. So how exactly do I find the x-coordinate here? What you do is you find the derivative, right? So find the derivative of f. So we know that f prime of x equals -2x. Now, what exactly do you set your derivative equal to? It's tempting to just say 0. You set the derivative equal to 0. Well, that's if you're finding like critical points, critical numbers. That's if you're using Rolle's theorem. But if you're playing with MVT, not necessarily. If you're playing with MVT, then what you do is you find the derivative and you set the derivative equal to the slope, in this case, of the secant. What was the slope of the secant line? The slope of the secant line was -1. And I'm going to set my derivative equal to -1 because what exactly does the derivative represent? the derivative can reveal the slope of your tangent. And I want my tangent to be parallel to my secant. And lines that are parallel, from like freshman year math, lines that are parallel have the same slope. And so I take my derivative and I set it equal to the slope of the secant, which is -1. And that's why you get 1/2. So this guy here, that is that number C. And notice that 1/2 is between -1 and 2. So this here, this 1/2, this is the x coordinate of your point of tangency. But what's the y coordinate? Well, you take the 1/2 and you plug it in where? You take the 1/2 and you plug it into the original function on a calculator. 1/2 squared is 1/4. 5 minus 1/4 would be 19 quarters. And so now what we can do is we can write the equation of the tangent line, because we have a point and we have a slope of -1 because we want to be parallel to the secant. And so your tangent line would be y minus y1 equals m times x minus x1. So this would be the equation of the tangent line. Now before you go, please stick around for 30 more seconds. I want to explain this to you. Here, if you open up a textbook, it's going to say this. But I want you to see what this is. This here is the derivative. And c is the number that we discovered. What exactly is this here? You know what this looks like on the right-hand side? That stuff on the right-hand side, you know what it looks like? It looks like middle school. Remember middle school? The formula for the slope between 2 points, which we did over there? y2 minus y1 over x2 minus x1. That's this guy, right? This is y2 minus y1. This is x2 minus x1. Because this is an x coordinate, and this is an x coordinate. And then f of this and f of this are the y coordinates above. So MVT, here is the slope of the secant, and here is the slope of the tangent, and you want them to equal because you want the lines to be parallel, which has equal slopes. So this is always how these problems work. And try yours now, or try some other ones if you want, and let me know if you have any questions.